I think you can see the presentation. So I go very fast on the first slides. First one was with the list of the beneficiary of the project. And the very important aspect is that our countries share two borders, where I can anticipate we will perform a seismic risk assessment. The second one was the presentation of the campus team, which is composed by myself. I already mentioned my usual research activities, by our geotechnical engineer, Elisabetta, which is here near me. Then we have another structural engineer, Fabrizio Comodini, who is here. And then our psychologist, Elena Kamisaska, who is in charge of all the psychological aspects of the project. Then I was trying to explain the project, and I tried to assess the importance of the risk assessment in terms of mitigation strategies and in terms of effective management of the civil protection emergency. Then I was mentioning the second keyword, which is multidimensional, and it is referring to damage, because we are going to focus on two dimensions of damage produced by a seismic event. The first one is the dimension related to structural damages, such as this one or this one. And the second dimension is related to the psychological consequences of people involved, such as state of depression, anxiety, and post-traumatic stress disorder experienced by people involved by the seismic event. Okay, I was here before the interruption. The third important keyword of our project is explainable artificial intelligence. I'm sure that Francesco Pistolesi will explain us and will shed light for us on the explainable artificial intelligence. I'd like to mention here that we will use explainable artificial intelligence to associate each real structures with a class of structures based on similarity criteria of parameters, of technical parameters. We also will use it to associate each real family with a class of families based on similarity criteria from the psychological point of view. And then we will use explainable artificial intelligence to associate the losses with the predicted level of damages and to associate it with the level of damage with the psychological consequences for the individuals involved. The use of this tool has several advantages, such as the possibility to learn accurate function from data to correlate seismic event to the level of damage and to the level of the losses, and the possibility to make the risk assessment increasingly more accurate as new data will be available by introducing new data in the system. We can go now on the first dimension, which is related to structural damage. We will define a certain number of classes of structures. These classes are based on materials, dimension of the structures, time of construction, type of design code, and so on. And so we will have, for example, a certain class of masonry structure, which is a point of this set, a different set of different type of masonry structures, another set, and so on. For example, we will have a certain number of classes of reinforced concrete structures here. From this set of classes, we will extract representative structures, which we will call benchmark structures. And so we have a set with some point. Each point represents a benchmark structures, and we will have a certain number of benchmark structures which represent the classes that we previously defined. Then we will consider representative seismic actions in terms of design spectra, of response spectra, and or in terms of time history, P grand acceleration in function of time. And by means of structural analysis, we will evaluate the structural damages produced by the representative seismic action to the representative or benchmark structures. A very similar approach we will use for the psychological consequences, and in this case we need to define a certain number of classes of families, and these classes will be based on socio-demographic indicators such as the number of components, the level of education, the total income, and so on, and also based on psychological indicators such as mental health, disability, family relation, and so on. So we will have, for example, a class of family with a certain number of children, another type of family without children, and so on, a set of classes of family. From the classes of families, we will extract representative families, which will be called benchmark families. And each point of this set represents a benchmark, a benchmark family, which is representative of one class or of the previous set. Then we will consider the representative structural damages, which are the damages produced by the representative seismic actions on the benchmark structures. And by means of psychological analysis, it will be possible to assess the psychological consequences of the individuals involved in a certain seismic event. So by summarizing, we have the structural dimension here, we have the psychological dimension here, and we are going to perform a seismic risk assessment in a given area, in a given territory, and therefore to evaluate the risk for real structures and real families. So we will consider these structures and families and a certain number of expected seismic actions. We will use explainable artificial intelligence to establish similarity criteria between the real structures and families and the benchmark structures and family. For example, we can have a certain structure here in the yellow bullet, and the psi will define that the structure is, for example, similar to this one. Similarly, the psi will consider the family in the structure, who lives in the people who lives in the structure, and will establish that this family is similar to one of the considered benchmark structure. Therefore, the damages of the benchmark structures can be associated to the damage of the real structures, and also the psychological consequences of the earthquake will be associated to the consequences for the real family. And this is the risk assessment, including the psychological damages and losses. This is the case when the explainable artificial intelligence can find a benchmark structure, a benchmark family similar to the real ones. But we can also, and in this case, we use the current knowledge base to assess the consequences of the seismic action. But we can also have a case where we have a structure which is not so similar to one or some of the benchmark structures. And the same can happen for the family, and so the family is not similar to the benchmark families. In this case, we have two possibilities. The first is to consider the most similar structure and family to the real ones, and so use again the current knowledge base to assess the risk assessment, which will be based to the damages and losses of similar structures and families. Another possibility will be to add new structures and new family in the benchmark sets. In this case, the performance of the seismic risk assessment will be based on an increased knowledge base, and therefore it will be more accurate. And this new increased knowledge base can be used for further seismic assessment when the system is used to detect the risk assessment, to find the risk assessment in further areas. During our project, we will perform the risk assessment in two cross-border pilot areas. if we observe the big ground acceleration map of our country, and we overlap this hazard map with the border among our country, we can observe that we have very high risk seismic regions near our borders, and for this reason we will select pilot areas and we will perform seismic risk assessment at the border between Italy and Slovenia, and well, I mean, not near the border, in a region near the border between Italy and Slovenia, and near the border between Slovenia and Croatia. The main outcomes of our project are the web application, which implements the system that we will develop. This web application will remain online after the end of the project and can be improved by adding benchmark classes and benchmark families, thus improving the reliability of the risk assessment during time. We will also produce a guideline and tutorial for the use of the web application when the current knowledge base is used to perform the risk assessment. We will also produce a guideline for the identification of the most vulnerable families to seismic events. And finally, a guideline for when we want for people who want to use the system by adding new classes, new classing, new benchmark structures, and new classes and new benchmark families. Another important outcome is the performance of the risk assessment in 2 cross-border areas. This will enhance the cross-border cooperation in crisis management and also will promote the sharing of knowledge among all of us. As I mentioned before, we are 4 beneficiaries, and we are all involved in the actions provided by the project. But the beneficiaries are also supported by the Civil Protection Authority of our 3 countries, by the Association of Italian Municipalities, and this will be very important for the pilot studies, because they will help to collect the data of the territory where the seismic risk assessment will be performed. We are also supported by the Italian Society for the Study of Traumatic Stress, and their help will be very useful for the assessment of the psychological analysis and in the drafting of the psychological guidelines. And also, we are supported by Stella Maris Foundation, which is the Scientific Institute for Childhood and Adolescent Neuropsychiatry, and the collaboration with Stella Maris will be also very useful for the psychological aspects of our project. Finally, I would like to go back to a previous slide with the importance of the seismic risk assessment to try to identify potential end users of our system. We have seen that the risk assessment is very important for planning mitigation strategies and for the management of the civil protection emergency. In the case of the mitigation strategies, the most important end users are the public administration, which will have a tool to detect a critical situation, to identify poor and old structures which need to be strengthening in order to increase the capacity against the seismic action. This will allow a rational use of the economic resource, and this can be done using the current knowledge base, or can be also improved in time by adding new structures and improved knowledge base. On the side of the civil protection, on the side of the management of the emergency, the main end user is the Civil Protection Authority, which can be use the system to define optimal emergency management based on reliable damage scenarios. So, and this, as also this morning we saw, this could include the planning of the psychological support for people involved by the seismic event. So that's all. I thank you very much. I'm sure that it will be very heavy to do this project, but I'm sure that with the help of all of us, we can we can achieve a very nice result. I hope, I think that we will do. And so thank you very much.
Thank you.